Hey everyone, welcome back to the channel. Today, we're diving into CycleGAN to transform Monet paintings into realistic photos. Imagine taking a masterpiece by Monet and reconstructing it as a real-world scene, all using deep learning. No paired examples, no manual labeling, just pure, unsupervised learning magic. We'll first understand the theory behind CycleGAN and then build it from scratch in PyTorch based on a Kaggle dataset. Let's get started. What is CycleGAN? CycleGAN, short for Cycle-Consistent Adversarial Networks, solves a very interesting problem. How do we translate images from one domain to another without needing perfectly paired data? In our case, we have a folder full of Monet paintings and a folder of real-world photos, but they aren't aligned one-to-one. CycleGAN handles this by enforcing two key ideas. Adversarial loss, making the generated images look realistic enough to fool a discriminator. Cycle consistency loss, ensuring that when you map an image to the other domain and then back again, you retrieve the original. That cycle constraint is what keeps the transformation grounded and meaningful. In simple terms, if you transform a Monet painting into a photo and then transform it back, you should get back the original Monet painting. How does CycleGAN work? The CycleGAN architecture consists of four key components. Generator G translates Monet to photo. Generator F translates photo to Monet. Discriminator D_X distinguishes real Monet paintings from fake ones. Discriminator D_Y distinguishes real photos from generated photos. During training, we fool the discriminators using adversarial loss. We enforce cycle consistency, meaning if we map Monet to Monet, it should come back to the original. We also add an identity loss to help preserve colors and details. For this project, we're using the Monet JPG and Photo JPG dataset from Kaggle. It includes about 1,500 Monet-style paintings, about 7,000 real-world photographs. Remember, the images are unpaired, meaning we don't have a one-to-one mapping between each painting and a real photo. CycleGAN architecture. Let's break down the CycleGAN architecture. We have two generators. G, Monet to photo. F, photo to Monet. And two discriminators. D_photo distinguishes real photos from fakes. D_Monet distinguishes real Monet paintings from fakes. The key idea is, take a Monet painting, generate a photo, translate that photo back to a Monet painting. Ensure the reconstruction matches the original painting. The same happens the other way too. Adversarial loss plus cycle consistency equals strong learning without paired data. Our generator uses a ResNet architecture. Initial downsampling layers. Multiple residual blocks help to preserve important features. Upsampling layers to reconstruct the output image. This architecture allows detailed translation between Monet and photo domains. The discriminator is based on a patch giant. Instead of deciding whether an entire image is real or fake, it decides whether small patches are real or fake, making it excellent at capturing textures. Now, let's build the CycleGAN step-by-step in PyTorch. This code implements a CycleGAN model, which learns to translate images from domain A, Monet paintings, to domain B, real photos, and vice versa, without needing paired data. The key idea of CycleGAN is cycle consistency. If we translate an image from A to B and back B to A, we should get back the original image. Thus, we build two generators. G_AB maps images from domain A to domain B. G_BA maps images from domain B to domain A. Two discriminators. D_A distinguishes real A images versus fake A images, generated by G_BA. D_B distinguishes real B images versus fake B images, generated by G_AB. First, we import PyTorch for deep learning, NumPy for numerical operations, OpenCV for image processing, although not heavily used here, Matplotlib for displaying generated images, A residual block is used inside the generator's middle layers to help the network learn identity mappings more easily, important for keeping structure during image translation. Reflection padding, padding the image by mirroring pixels at the borders, helps reduce boundary artifacts during convolution. ConV2D, kernel size, 3 extract local patterns. Instance norm 2D, normalizes the image separately for each instance and channel. Better than batch norm for style transfer tasks. ReLU, nonlinear activation. Skip connection, return x plus self.block, x. Adds input to output, residual connection. Helps training deeper networks without vanishing gradients. This defines the generator network, maps images from one domain to another. The structure. Initial convolution layer expands channels. Downsampling reduces spatial dimensions to understand bigger picture. Residual blocks preserve content while allowing stylistic changes. Upsampling restore original size. Output layer generates the translated image. Details. Initial convolution uses reflection padding and instance norm. Downsampling is done using stride, 2 convolutions. Upsampling is done using bilinear interpolation followed by convolution. Output uses tan activation to scale pixel values between -1, 1. Discriminator tells if an image is real from training data or fake generated. Structure. Sequence of convolutional layers. Each layer downsamples the input, stride equals 2. Instance norm applied after convolution, except first layer. Leaky ReLU activation, better for stabilizing GAN training. At the end, 0 padding slightly adjusts size. Final convolution outputs a patch of real/fake scores, PyTorch. Important note on PyTorch. Rather than giving a single real/fake score for the whole image, PyTorch outputs a matrix. Each patch, small region, of the image is judged independently. Helps discriminator focus on fine texture details. CycleGAN uses a combination of 3 losses. Adversarial loss, fool the discriminator. Cycle consistency loss, translate, monate to photo to monate, and then reconstruct the original. Identity loss, prevent unnecessary changes when the input is already close to the target domain. These combined allow the model to generate both realistic and consistent outputs. We initialize 2 generators and 2 discriminators, each operating on 3-channel RGB images. Also move to CUDA, GPU, if available. We use Atom Optimizer for both generators and discriminators. With settings tuned for stability, small learning rates, and beta equals 0.5. Images from Monate paintings and real photos are loaded using a custom image dataset class. Images are transformed. Random horizontal flip. Normalization to -1, 1. To tensor. Function to display. Real A, fake B, real B, fake A. Helps visually inspect the quality of generation during training. In the training loop, we generate fake images from real ones. Calculate all losses, adversarial, cycle, identity. Update the generators and discriminators separately. Save generated samples for visual monitoring. The process repeats across multiple epochs to improve image quality. For each epoch and each batch. Instead of using one-hot vectors, which are for classification, here real/fake labels are tensors filled with 1 or 0 for regression MSE loss. Train generators. Steps. Set generators to train mode. Generate fake images. Fake_B equals G_AB real_A. Fake_A equals G_BA real_B. Identity loss. Make sure G_AB real_B is almost equal to real_B and G_BA real_A is almost equal to real_A. GAN loss. Try to fool the discriminators, make D think fakes are real. Cycle consistency loss. Ensure real_A to fake_B to recovered_A is almost equal to real_A. And real_B to fake_A to recovered_B is almost equal to real_B. Combine all. Backpropagate and update generator parameters separately for D_A and D_B. Maximize the ability to distinguish real from fake. Loss is average of real and fake classification errors. Detach the fake images to avoid updating the generator during discriminator training. Schedulers update the learning rate gradually after decay_epoch. Every 10 epochs. Show generated images using sample_images. Print current losses. After training, here's what we get. Real-world photos that look like Monet masterpieces. Monet paintings that look almost photorealistic. Pretty amazing, right? All this without any paired training data. Finally, load images from photo dataset. Pass through G_BA, photo to Monet generator. Save the generated Monet-style images to disk. Zip the folder if needed. And that's it. You just built a full CycleGAN that transforms Monet paintings into real-world photos. CycleGANs are an incredibly powerful tool, unlocking image-to-image translation without requiring paired datasets. If you enjoyed this walkthrough, please smash that like button, subscribe to the channel, and stay tuned for more AI magic. Thanks for watching, and I'll see you in the next one.